with a radius approximately 1.4 times that of Jupiter. Despite its size, it orbits its star at an extremely close distance of just 0.045 astronomical units, AU, which is 1/8 the distance between Mercury and the Sun. This proximity results in extreme atmospheric heating, with temperatures soaring to around 1000 degrees Celsius 1800 degrees Fahrenheit, making it a classic hot Jupiter. One of the most remarkable aspects of this exoplanet is its atmosphere. It was the first where scientists directly detected atmospheric components using spectroscopic observations during transits. Sodium was the first element identified, offering an initial glimpse into its composition. Later studies revealed the presence of water vapor, methane, and carbon dioxide, making it the first exoplanet with a multi-component atmospheric analysis. Another crucial discovery related to HD 209458b was its atmospheric escape. Observations from the Hubble Space Telescope revealed that the intense radiation from its star is stripping away the outer layers. This process, known as hydrodynamic escape, has created an enormous cloud of hydrogen trailing the planet, resembling a comet's tail. Due to this phenomenon, it was dubbed an evaporating planet. The estimated escape rate is about 10,000 tons of hydrogen per second, a significant loss, yet not enough to deplete its mass within billions of years. The planet has also played a major role in understanding cloud formation in extreme environments. Hazes and potential cloud structures inferred from its spectrum suggest the presence of scattering particles in its upper atmosphere. These findings have provided valuable insights into the physics and chemistry of exoplanetary atmospheres, helping refine models for other distant worlds. Another fascinating aspect of HD 209458b is its orbit. With an incredibly short orbital period of just 3.5 days, its proximity to the star generates strong tidal forces, likely causing it to be tidally locked. This means one hemisphere is in perpetual daylight while the other remains in eternal darkness. The extreme temperature gradient between the two sides results in violent atmospheric dynamics, including supersonic winds that redistribute heat. Beyond its scientific contributions, this exoplanet has played a key role in advancing observational techniques. Its discovery pushed the limits of spectroscopy, transit photometry, and atmospheric modeling. Initially confirmed via the radial velocity method, which detects a star's wobble due to an orbiting planet's gravity, it was later studied using both radial velocity and transit methods. This dual approach allowed for unprecedented precision in determining its mass, radius, and density, setting a new standard for exoplanet research. HD 209458b has also provided crucial insights into planetary formation and migration. Theories suggest that hot Jupiters like this one did not orbit but migrated inward after forming farther from their stars. The exact mechanisms, whether interactions with a protoplanetary disk or gravitational influences from other planets, remain an active area of research. Studying this planet and similar models of planetary evolution. Another intriguing challenge posed by this exoplanet is its unexpectedly large size. Its radius exceeds predictions based on standard planetary models, an issue known as the radius anomaly, which is common among hot Jupiters. Several explanations have been proposed, including its sources, where magnets between the planet and its star generate. Continued research on HD 2058b provides valuable clues about these complex processes. Beyond its direct scientific impact, this planet has become an operational symbol in the search for extraterrestrial worlds. Its discovery and subsequent revelations about its atmosphere, orbit, and physical properties have captivated both scientists and the public. As a pioneering exoplanet, it represents how far humanity has come and expands beyond our solar system. In conclusion, HD 209458b remains a landmark discovery in modern astronomy. Its detection marked the beginning of a new era in exoplanetary science, and its detailed study has provided essential knowledge about planetary atmospheres, migration, and evolution. As a hot Jupiter gradually losing its atmosphere to its star, it serves as a natural laboratory for studying extreme planetary environments. The legacy of this exoplanet lies not just in what it has taught us about a single world, but in how it has paved the way for the exploration of countless others across the galaxy. HD 209458b is one of the most well-documented and fascinating exoplanets ever discovered. Orbiting the star in the constellation Pegasus, this gas giant is located approximately 150 light-years from Earth. Its discovery in 1999 was groundbreaking, as it became the first exoplanet transiting its host star. This key observation allowed scientists to study not only its orbit but also its physical and atmospheric characteristics in unprecedented detail, making it a cornerstone in the history of exoplanetary science. Often referred to as a pioneering hot Jupiter, HD 209458b has a mass roughly 220 times that of Earth, or about 0.7 times that of Jupiter. However, its radius is significantly larger, approximately 1.4 Jupiter, classifying it as an inflated planet. This unexpectedly large size and low density challenge conventional models of planet and structure. Researchers suspect that the intense stellar radiation from its host star and its close proximity may contribute to this inflation observed in many hot Jupiters. The exoplanet follows an extremely tight orbit, circling its star at just 0.045 astronomical units (AU), and completing a full revolution in only 3.5 Earth days. This close range exposes it to immense stellar radiation, heating its atmosphere to over 1,000 Fahrenheit. Heat causes the atmosphere to expand and escape, earning it the classification of an evaporating planet. Observations from the Hubble Space Telescope show a cloud of hydrogen, along with traces of oxygen and carbon behind the planet like a comet's tail. This large-scale atmospheric escape provides valves into the planetary atmospheres. The atmospheric composition of this exoplanet has been a major focus of scientific research. It was the first where atmospheric components were directly detected, setting a precedent for the study of exoplanetary atmospheres. Early observations identified, but later studies revealed a more complex mix, including water vapor and carbon dioxide. The detection of water vapor was particularly significant, as it marked the first confirmed presence of water on a planet outside the solar system. This finding demonstrated the potential for detailed atmospheric analysis of exoplanets, even those located light-years away. Beyond its chemical composition, the planet's atmosphere exhibits extreme physical dynamics. It is believed to be tidally locked, in constant daylight, while the other remains in perpetual darkness. This sharp contrast creates a dramatic temperature gradient, generating supersonic winds that may reach speeds of up to 7,000 kilometers per hour, 4,350 miles per hour. These winds redistribute heat across the leading to turbulent and complex weather patterns. Observations have also suggested the presence of high-altitude clouds and hazes, further complicating its atmospheric behavior. The study of HD 209458b has provided crucial insights into planetary migration. Current models suggest that hot Jupiters like this one did not form in their present orbits but instead migrated inward after forming farther from their stars. The mechanisms responsible for this migration, whether with a protoplanetary disk or gravitational influences from other celestial bodies, remain an active area of research. The extreme proximity of this exoplanet to its star challenges existing theories and continues to prompt new investigations into the forces shaping planetary systems. Another enigmatic aspect of this world is its unexpectedly large radius. Standard planetary models struggle to explain this inflation, as its size exceeds expectations based on its mass and temperature. Possible explanations include tidal heating, where gravitational interactions with the host star generate internal heat, or ohmic dissipation, a process in which the planet's magnetic field interacts with ionized gases in its atmosphere, converting kinetic energy into thermal mechanisms behind main a subject of ongoing research. This exoplanet has also played a key role in advancing astronomical observational techniques. Its discovery and subsequent characterization relied on a combination of the radial velocity and transit photometry. The radial velocity method detects the gravitational wobble of a star caused by an orbiting planet, while the transit method measures the dip in a star's brightness as the planet passes. Together, provided extensive details about the planet's mass, radius, orbital period, and atmospheric properties. This dual method approach has since become a standard in exoplanetary research, facilitating the discovery and analysis of thousands of distant worlds. The significance of HD20 extends beyond its own unique characteristics. Its discovery and extensive study have paved the way for further exploration of exoplanets, inspired of new objects and mission. For example, the J telescope, JWST, is expected to build upon its legacy by offering even more detailed observations of exoplanetary atmospheres. The techniques used to analyze this gas influenced the design of objects, such as the European Space Agency, which aims to examine the atmospheres of hundreds of exoplanets. In conclusion, HD 20945, often referred to as the evaporating planet, the roaster world, or the inflated gas sphere, remains a landmark in the study of exoplanets. Its discovery marked the beginning of a new astronomy, while its detailed characterization has provided unparalleled insights into planetary atmospheres, migration, and evolution. As one of the most thoroughly studied exoplanets, it continues to serve as a natural laboratory for exploring the physics and chemistry of extreme planetary environments. Its legacy is not only in what it has revealed about its own unique properties, but also in its role as a catalyst for the exploration of countless other worlds across the galaxy. HD 209458b continues to be a cornerstone of exoplanetary science, inspiring new generations of research into planetary systems beyond our own. Its atmospheric properties, orbital mechanics, and contributions to advancing observational techniques provide a near-endless array of opportunities. Scientists see exoplanet as a proving ground for refining methods that characterize not only fundamental parameters, but also their complex behaviors and interactions with their host stars. One of the most remarkable aspects of this boiling exoplanet is its evaporating atmosphere. The hydrodynamic escape of hydrogen, oxygen, and carbon detected from the planet provided the first direct evidence of large-scale atmospheric loss on an exoplanet. This phenomenon has significant implications for understanding the long-term evolution of planetary atmospheres, particularly for those in close proximity to their stars. Atmospheric escape can strip smaller planets of their gaseous envelopes entirely, potentially leaving behind barren rocky worlds. Studying this extreme case allows scientists to model the process under the most intense conditions, offering valuable insights applicable to a broad range of planetary systems. Beyond atmospheric loss, this exoplanet serves as a fascinating case study for tidal locking dynamics. Likely locked in a synchronous orbit, one hemisphere remains in constant daylight, while the other is permanently shrouded in darkness. This configuration results in extreme thermal contrasts, with the day side reaching blistering temperatures, while the night side remains significantly cooler. The redistribution of heat between these two hemispheres is facilitated by supersonic winds, driven by intense stellar radiation. These high-speed currents transport energy across the planet, influencing its overall atmospheric structure and by interactions. Researchers gain valuable insights into atmospheric behavior under extreme tidal locking conditions, which is also relevant to rocky exoplanets in habitable zones. The inflated size of HD 2093 remains another puzzle. Its radius exceeds the predictions for a planet of its mass, leading to ongoing debates about the mechanisms responsible for this anomaly. Tidal heating, caused by gravitational interactions with its star, may generate sufficient heat to expand its gaseous envelope. Another possible explanation is ohmic dissipation, where interactions between the planet's magnetic field and ionized atmospheric particles produce additional heating. These processes, while still theoretical, highlight the complexity of planetary physics and the need for continued observations to understanding. This exoplanet significantly advanced our knowledge of atmospheric chemistry. The detection of sodium, water vapor, methane, and carbon dioxide in its atmosphere marked a turning point in exoplanet research. These discoveries, made possible through spectroscopy, have allowed scientists to analyze the starlight passing through the planet's atmosphere during transit. Absorption features in the spectrum. Researchers can identify specific molecules and estimate their abundances. This breakthrough not only provided a clearer picture of HD 209458b's atmospheric composition but also laid the groundwork for studying atmospheres on smaller and potentially habitable exoplanets. Another key contribution of this planet is its role in understanding planet-star interactions. Intense radiation and stellar winds from its host star play a crucial role in driving atmospheric escape. These forces also influence its magnetosphere, which helps shield the planet from high-energy particles. Examining its magnetic environment provides valuable insights into how planets in extreme conditions protect themselves from stellar radiation. Such studies have broader implications for assessing the habitability of planets orbiting active or young stars. HD 209458b has also deepened our understanding of planetary migration. Hot Jupiters like this one are believed to form much farther from their stars in colder regions before migrating inward. mechanism behind, whether through protoplanetary disk, gravitational perturbations from other celestial bodies, or a combination of factors, remains a topic of active research. The orbital properties of this gas, combined with its atmospheric and physical characteristics, provide critical data for refining these theories. Additionally, the presence of high-altitude hazes and clouds in its atmosphere has enhanced our understanding of aerosols in exoplanetary environments. These hazes scatter light and obscure certain spectral features, complicating the detection of atmospheric molecules. Affects scientists to develop models that improve the accuracy of atmospheric retrievals for other exoplanets. This research is crucial for upcoming missions aiming to characterize the atmospheres of Earth-like planets, where clouds and hazes may similarly impact observations. This giant close-in planet also serves as a natural laboratory for studying extreme stellar irradiation. The intense heat it experiences profoundly impacts its atmospheric chemistry, potentially triggering photochemical reactions that produce exotic molecules. These processes are of great interest to researchers studying planetary chemistry across a range of conditions, including those found on temperate worlds. Finally, the cultural and scientific legacy of HD 20945AB cannot be overstated. As the first transiting exoplanet ever discovered, it has inspired and role in shaping modern exoplanetary. Its detection marked the where detailed of distant planets became possible. The techniques refined through its study have since been applied to thousands of other exoplanets, broadening our understanding of the diverse planetary systems within our galaxy. In summary, 20945AB, often referred to as the boiling gas giant, the evaporating planet, or the roaster world, remains a fundamental target in exoplanetary research. Its unique characteristics, from atmospheric escape to extreme weather patterns and inflated size, have provided unparalleled insights into planetary physics, chemistry, and evolution. As a trailblazing exoplanet, it continues to drive new discoveries and innovations, cementing its legacy as a key stepping stone in our quest to understand the cosmos. HD 20945AB, known by many Osiris, or the inflated giant, is far more than a scientific curiosity. It stands as a beacon, illuminating the vast, complex, and untamed world of exoplanets. While much of its physical nature has been extensively studied, lingering mysteries and tantalizing possibilities continue to intrigue scientists. We probe into its secrets, the more it reshapes our understanding of planetary science, reminding us of how much more remains to be uncovered. One of the most fascinating aspects of this exoplanet is its role as the prototype for studying atmospheric escape. When the Hubble Space Telescope first detected hydrogen being stripped from its upper atmosphere, forming a massive comet-like tail, it opened an field of research. But this process isn't just about mass loss, it's about the planet, a slow yet steady evolution, sculpted by its star's intense ultraviolet. This is profound questions. Is it in a transient destined to become something entirely different in millions of years? Could it eventually shrink into a rocky core, resembling a super-Earth or a mini-nebula of its gaseous envelope? Even more captivating is the planetary alchemist. Under the relentless glare of its star, molecules in the atmosphere are broken apart. Action play between radiation and chemistry may produce exotic cannot form under any other conditions. Could its atmosphere harbor unexpected molecular treasures, rare metallic vapors or charged plasma layers that challenge existing chemical models? Some researchers even speculate that such extreme environments might offer clues about how complex molecules form in space, potentially shedding life. Beyond its atmospheric escape, HD 209458b is a case study in exoclimatology. Earth's climate is shaped by relatively mild interactions between the Sun and atmosphere. Conditions here are defined by extremes. The scorching heat of its day side and the stark chill of its night side create a planetary furnace, with supersonic winds exceeding 7,000 kilometers per hour, 4,000 miles per hour. What's really happening in those winds? Could they be mixing atmospheric layers in ways that defy our models? Could they transport elements or compounds in patterns that mirror, but vastly amplify, the jet streams and ocean currents of Earth? Perhaps one of the most provocative questions concerns its long-term fate. If the planet's atmosphere continues to erode of years, what will remain? Current estimates suggest it is losing around 10,000 tons of hydrogen every second. While this rate is insignificant relative to its total mass, it could one day reveal a hidden core. What lies beneath the thick layers? Is it a solid core of rock and metal, or something more exotic? Could this once blazing gas giant eventually become a barren, rocky world, an artifact of its tumultuous history? HD 2094 also challenges traditional planetary classifications. In our solar system, planets neatly fall into rocky worlds or gas giants, but this exoplanet doesn't fit so easily. Its diffuse, oversized atmosphere is more reminiscent of a star's corona than a conventional planetary. Could it represent an intermediate stage between planets and failed stars like brown dwarfs? Does it challenge us to redefine stories altogether? The mystery deepens when considering its inflated size. Traditional models of planetary formation and structure struggle to explain why its radius is significantly larger than expected. Could unknown processes be at work within its interior? Some theories suggest that tidal forces from its close orbit generate immense internal heat, expanding the planet. Others propose that magnetic interactions with charged atmospheric particles create additional energy, keeping it puffed up. What if these theories only scratch the surface? Could this planet hold the key to uncovering new physics governing planetary interiors? Then there is the enigma of its clouds. Observations suggest high-altitude hazes composed of exotic materials like silicates or metals. These particles may scatter light in unexpected ways, creating spectral signatures that puzzle us. Are these forming and dissipating with the planet's violent winds? Or are they a permanent feature, shielding deeper layers from observation? Their presence may be both a barrier and a window into the planet's secrets. Beyond its scientific importance, HD 209458b holds cultural significance as well. As the first transiting exoplanet ever discovered, it opened the door to a universe of possibilities. Its detection revolutionized astronomy, way for missions like Kepler and the James Webb Space Telescope, which now is of exoplanetary research. This world story is not just one of science, it is one of humanity's unrelenting curiosity and for the unknown. There is a rising possibility that this gas giant is not alone. While no addition confirmed in its cylinder often hints at a Morcary arrangement. Could smaller, rocky worlds be orbiting farther out, hidden from current detection methods? Has the migration atmospheric loss of HD 209458b influenced its hypothetical neighbors, their orbits and the possibility of an unseen planet only adds to its allure. In many ways, this exoplanet is not just a world, it's a puzzle, a paradox, and a promise of future discoveries. It has already revolutionized our understanding of distant planets, yet it continues to pose new questions at every turn. Every observation, every model, and every theory brings us closer to unraveling its mysteries, yet new enigmas always emerge. HD 209458b stands as a testament to the infinite complexity of the cosmos, a world that challenges our assumptions and fuels our imagination. It is a reminder that the universe is far more dynamic, diverse, and surprising than we ever dared to dream. And perhaps, hidden in its fiery winds and evaporating atmosphere, lies the next great revelation in our quest to understand the stars. HD 209458b, often hailed as the trailblazer of exoplanets, is more than a scientific curiosity. It is a gateway to understanding the extremes of planetary science. While much has been revealed about this enigmatic world, each new discovery seems to unveil yet another layer of complexity, keeping astronomers captivated. The very essence of Osiris lies in its dynamic nature, a planet in transition, constantly reshaped by the intense forces that play within its star system. This ongoing transformation provides a natural laboratory for exploring planetary evolution, atmospheric physics, and even the boundaries of what defines a planet. One of its most mesmerizing features is the vast, comet-like tail of hydrogen trailing behind it, a direct consequence of atmospheric escape. Observations of this phenomenon have allowed astronomers to quantify loss, providing unprecedented insights into how stellar radiation interacts with planetary atmospheres. However, the loss of hydrogen is only part of a larger story. Recent studies suggest that heavier elements, such as oxygen and carbon, are also escaping, albeit at lower rates. This evolution raises questions how long the planet can sustain the envelope and what might be revealed beneath. Atmospheric loss is not just an interesting feature, it could redefine the planet's future. Could HD 209458b eventually shed its entire atmosphere, leaving behind a dense, rocky core? If so, what would this exposed remnant look like? Would it resemble the scorched rocky planets observed in other star systems, or could it be entirely unexpected? Some theorists speculate that stripped-down remnants of gas giants might evolve into certain types of super-Earths, bridging the gap between terrestrial and gaseous planets. If Osiris is indeed undergoing such a transformation, it could offer a rare glimpse into a transitional phase of planetary development. Even as its atmosphere thins, the interactions between the planet and its star continue to reveal stunning details about extreme environments. The close orbit exposes stellar winds and generating a unique interplay between the planet's magnetic field and charged particles from the star. Some models suggest that Osiris might generate auroras far more powerful than those seen on Earth or Jupiter. These massive, planet-wide auroras could glow faintly in exotic colors, fueled by ionized gases in the upper atmosphere. While we cannot yet directly observe these phenomena, they hint at the complex electromagnetic environment surrounding this distant world. The planet's inflated size remains an enduring mystery. Despite decades of study, scientists are still working to determine why it defies theoretical predictions of planetary radii. One leading theory suggests continuous tidal flexing, where gravitational forces between the planet and its star generate heat deep within, causing atmospheric expansion. Another hypothesis points to ohmic dissipation, where interactions between magnetic fields and ionized gases convert kinetic animal energy. Understanding these processes our knowledge of Osiris but also provides valuable insights into other inflated hot Jupiter. Osiris's atmosphere is another source of intrigue, particularly chemical processes. Observations have confirmed the sodium, methane, and carbon, but the true excitement lies undiscovered. The relentless radiation from its star-like reactions with compounds, such as metal carbons. These molecules only in trace amounts, but they could provide crucial clues about the interplay between radiation and chemistry in extreme environments. Furthermore, the presence of hazes complicates atmospheric study. These aerosols scatter light and obscure spectral features, making it difficult to probe. What are these hazes? Could they contain silicate particles, metallic compounds, or even unidentified materials? The dynamics are puzzle. Tidal locking creates a stark temperature contrast between the blizzard and the tide, resulting in violent weather patterns. Supersonic winds sweep across the radiation, transport heat unevenly, forming shifting hot spots that challenge models. Could these dynamic processes create temporary regions of stability in an otherwise chaotic atmosphere? If so, what unexpected chemical interactions might occur in these transient zones? Perhaps most intriguingly, some aspects of 09458b still defy explanation. Despite advancements in exoplanetary science, some observations of Osiris remain inconsistent with existing models. For example, the observed hydrogen loss rate is higher than predicted, suggesting that additional factors, such as stronger than expected magnetic interactions or previously unknown atmospheric mechanisms, could be amplifying the escape process. Alternatively, entirely new physical processes may be at work, waiting to be discovered. The influence of this exoplanet extends far beyond its own system. As the first transiting exoplanet ever revolutionized astronomy and paved the way for nearly every major exoplanetary mission since. Instruments like the James Webb Space Telescope and the European Space Agency's Ariel mission are beneficiaries of the techniques pioneered during its study. These missions aim to build on a legacy by spheres of smaller, cooler planets, including potentially habitable worlds. In this study of 09b has brought us closer to answering one of humanity's most profound questions. Are we alone in the universe? Yet, even as we look to the future, Osiris reminds us of the importance of revisiting what we think we know. Each new observation has the potential to overturn previous assumptions, revealing deeper complexities. Advances in high-resolution spectroscopy have already detected subtle shifts in atmospheric composition, suggesting that the planet's chemistry may evolve over time. Could these changes be driven by seasonal variations on Earth, or are they solely the result of differences, such as fluctuations in scientific significance planet but weight. It is not just an object of study but a story, a narrative of transformation, survival, and the relentless interplay of forces that shape the cosmos. Planets are not static entities but dynamic worlds, constantly evolving in response to their environments. Osiris challenges us to think beyond the familiar planetary systems that operate under entirely different rules, and to embrace the infinite diversity of the universe. As telescopes grow more powerful and observational techniques more refined, the mysteries of HD 9458b will continue to unfold. With its boiling atmosphere, violent winds, and evolving will remain a focal point for scientific exploration, a world that refuses to fit neatly into existing categories and is the boundary. In the vast expanse of the cosmos, it stands as a beacon of reminding most things has to inspire us, and HD 209458b, often referred to as Osiris, continues to captivate astronomers with its defiance of convention and the mysteries it refuses to fully reveal. This blazing titan, locked in an eternal gravitational embrace with its star, is more than an object of study, a cosmic enigma. Structure challenge fundamental assumptions as to wonder how much more this planet has to teach us, and what answers it might hold to questions we ask. One of its most is its precarious existence. Pure stability can be defined for a world that is getting its atmosphere in constant conflict with its environment. Every second, thousands of tons of hydrogen escape into space, a relentless loss that should, in theory, spell its demise. Yet, despite this the planet endures. Could an unknown stabilizing factor be at play, or is this merely a temporary stage in its transformation? The conditions it endures are: day side is heated to temperatures high enough to vaporize rock. Night side experiences chaotic winds that redistribute heat into darkness. Atmospheric pressures reach such intensities that even hydrogen, typically the lightest and most elusive of gases, forms dense, massive layers. Could these deep regions harbor exotic states of matter, such as metallic hydrogen, conducting heat and electricity in ways unimagined? If so, this planet may serve as a laboratory for entirely new realms of planetary physics. Its atmosphere, constantly bombarded by ultraviolet and X-ray radiation, undergoes violent transformations, breaking apart molecules, unpredictable chemical reactions. This relentless may be forging rare or even unknown compounds, synthesized in an environment unlike any in the solar system. The search for these exotic molecules pushes the limits of spectroscopic technology, as scientists attempt to extract faint chemical signatures hidden within observational data. Beyond its internal turmoil, the relationship with its parent star adds another complexity. Radiate atmospheric forces create oscillations detectable from light years away. Some theorists suggest that extreme tidal interactions could the star's outer layers cause disturbances. If true, this would mean the planet is not merely a passive recipient of its star's influence, but an active participant in shaping the system's dynamic. The presence of a magnetosphere, if confirmed, could be another crucial factor in understanding its long-term survival. A strong magnetic field might deflect a portion of the stellar wind, slowing atmospheric escape. But this protective barrier could come with its own consequences. Interactions between magnetic fields, charged particles, and ionized gases might generate immense currents and even planetary-scale lightning storms. Though invisible from Earth, such phenomena could turn the planet into a world of light, where flashes of electricity illuminate its turbulent skies. For all its chaos, there may be underlying patterns at work. Infrared observations indicate that heat distribution across the surface is random as previously thought. Hot spots appear slightly off-center from expected locations, hinting that high-speed winds are shifting energy in complex and unexpected ways. The movement of these zones over time suggests that the atmosphere functions like a vast, dynamic influenced by forces still not fully understood. Are these shifts driven by internal atmospheric dynamics, or do they respond to changes in the star's activity? Its current orbit raises further questions. A planet this large, this close to its star, likely did not form in place. Instead, it must have migrated inward from a more distant, stable region. What caused this journey? Did it once have a planetary sibling that was ejected from the system, or was it drawn inward through interactions with the protoplanetary disk? If this migration was as dramatic as some models suggest, it could have destabilized other planets in the system, leaving behind a history of gravitational upheaval. Could this be the lone survivor of such an event, bearing scars of a violent past? Looking ahead, this planet may serve as a glimpse into the future of other worlds. As stars age and swell into red giants, they unleash even greater radiation upon their planetary systems. For a world already enduring extreme conditions, this transformation could be catastrophic. Will it eventually be stripped entirely of its atmosphere, leaving behind a barren core adrift in space? Or will it adapt, clinging to some remnant of its original form in ways we cannot yet predict? Make it an invaluable model for studying planetary evolution, not just within its own system but across the galaxy. Even more spectacular layers of reality, fleeting regions where pressure and temperature align in ways formation of unusual compounds. Could these transient pockets offer insights into how atmospheres evolve under extremes. Intriguingly, might they provide analogues to the early rocky planets like Earth? If so, studying this hot Jupiter could unexpectedly help us better understand our own planet's past. Finally, there is the question of whether this world is truly an outlier. Thousands of exoplanets have been discovered since its transit was first observed, yet it remains among the most compelling. Is it a rare anomaly, or does it represent an entire class of planets so extreme that they push the boundaries of current classification? If the latter, what does this reveal about the chaotic, unpredictable nature of planetary formation? The more we learn, the clearer it becomes. Earth does not adhere to rigid structures but instead shaped by an intricate interplay of forces we are only beginning to grasp. The story of HD 209458b is far from over. Each new observation, theoretical breakthrough, and technological advancement adds another chapter to its narrative. It is a world of extremes, contradictions, and mysteries, one that refuses to conform to expectations and continuously challenges the limits of our understanding. As our ability to explore the cosmos advances, this planet serves as a reminder that even in the most inhospitable of the universe, discovery thrives. It is an proof that the pursuit of knowledge knows no bounds, and a testament to the boundless complexity of the cosmos. Whatever the future holds for the world, one truth remains: it refuses to be ignored. And as long as we seek to understand, it will continue to whisper its secrets to listen. The saga of HD 2098b is a narrative that grows more complex and fascinating. This boiling enigma has become a cornerstone of planetary science, a world that defies easy classification and challenges our understanding of the physical laws governing planetary systems. Even after observation and study, it continues to resist complete explanation. Captivate the cosmos. At the heart is the its host star. While its atmosphere steadily escapes into space, it appears to fight back, clinging to its gaseous envelope. Less ultraviolet radiation of war creates an extreme that it seems almost Yet, this very extremity makes it a scientific treasure trove. By studying this process of atmospheric erosion, scientists gain insights not only into this exoplanet's evolution but also into the fate of countless other worlds orbiting close to their stars. One particularly intriguing aspect of this atmospheric loss is the unexpected escape of heavier elements, such as oxygen and carbon. While hydrogen and helium are light enough to be carried away by stellar winds, the loss of denser elements suggests the influence of powerful forces in the upper atmosphere. Could magnetic interactions or mechanisms be at work? Understanding these processes could offer crucial clues about the long-term evolution of not just this planet, planet but also other hot Jupiters and even smaller rocky worlds. The atmosphere, a constantly shifting realm of chemical and physical chaos, continues to reveal surprises. Among the most significant discoveries is the presence of water vapor, detected through detailed spectroscopic analysis. This finding was groundbreaking at the time, yet water may be just the beginning. Extreme heat and radiation could be driving the formation of more complex molecules, perhaps even carbon-based compounds existing in unfamiliar forms. Could this environment harbor fleeting traces of prebiotic chemistry, or does its intensity erase any such possibility? The question fuels ongoing research, pushing scientists to refine their models of atmospheric behavior. The planet's weather patterns add another layer of intrigue. Winds here are unlike anything seen on Earth, reaching speeds that could encircle the planet in mere hours. These violent currents arise from the stark temperature contrast between the scorching day side and the relatively cooler night side. But recent models suggest that atmospheric dynamics may be even more chaotic than previously thought, with jet streams, vortices, and localized storms forming and dissipating in response to rapid rotation and intense stellar heating. If we could observe these phenomena directly, what would we see? Towering clouds of metallic vapor, cascading flows of ionized gases lit by electrical discharges. The very idea stretches the imagination. Beneath its thick, turbulent atmosphere lies a hidden core, a region beyond direct observation, but critical to understanding the planet's origins. Is it similar to Jupiter's, a dense mix of rock, ice, and metallic hydrogen, or something entirely different, shaped by the conditions of its migration and exposure to intense radiation? Some theorists speculate that the core may contain superionic water, a bizarre state of matter where molecules exist as both solid and fluid, conducting electricity with astonishing efficiency. If such an exotic form of water exists, it could dramatically influence the planet's magnetic field and internal structure. Speaking of magnetism, the presence of a magnetosphere remains a compelling mystery. While it has not been measured directly, a strong magnetic field would have profound implications for atmospheric escape and interactions with the star. If present, it could act as a shield, reducing reducing mass loss in certain regions, while simultaneously generating spectacular auroras. Planet-wide light shows far more intense than anything seen on Earth. Would these auroras glow in familiar greens, or would they take on more exotic hues, dictated by the unique chemistry of this alien world? The mystery extends beyond its atmosphere and internal structure to its very existence in its current orbit. It is unlikely that this gas giant formed so close to its star. Instead, it must have migrated inward from a more distant, cooler region of the system. But what triggered this journey? Was it gravitational interactions with the now absent planet, or was it drawn inward through a slow, chaotic dance with the protoplanetary disk? If its migration was as disruptive as some models suggest, it may have destabilized in the system, potentially leaving behind a history of destruction. Could it be the lone survivor, a world bearing the scars of a violent past? The possibility that's in the system remains an open question. While no other worlds have been its stars of a hot chance at a more complex planet. Could smaller, rocky hidden from our detection method, or is there evidence of their destruction? Unraveling this mystery could reveal whether it is a solitary wanderer, or part of a larger, unseen family. This exoplanet also forces us to think about the future, not just of this but of the planet as a whole. It advances in observational techniques, inspiring missions like the James Webb Space Telescope, which promises to deepen our understanding of distant worlds. But it also reminds us that every discovery is merely a door. What lies beyond this enigmatic planet in the uncharted frontiers of exoplanetary science? What await our detection, and what secrets will they hold? H09458b is more than just a planet, it is a symbol of a testament to the boundless creativity of the cosmos. It demonstrates that even in the harshest, most extreme environments, there is beauty, complexity, and the potential for discovery. As scientists continue to study this world and others like it, they are not just expanding our knowledge of they are also truths about our own place in the universe and the infinite possibilities that lie among the stars. 209,458b stands as a planet that appears to defy its while simultaneously thriving in the extreme conditions imposed by its star. The deeper scientists explore this enigmatic world, the more it reveals itself as a tapestry of unanswered questions, offering a kaleidoscope of possibilities far beyond its fiery skies. Every revelation about the exoplanet opens doors to new mysteries, ensuring that it will remain a centerpiece of planetary exploration for generations to come. One of the most compelling aspects is how it forces us to rethink planetary habitability and the far too life as we know as traditional planets can endure. Them defy expectations, persisting against incredible odds. Could the very process eroding its atmosphere chemical transformations that, in some distant way, resemble the early stages of prebiotic chemistry? These possibilities speculative boundaries considered possible in extreme environments. The creation remains tantalizing in planetary science. The idea that this roster world began its life in a much cooler region of its star system is widely accepted, but the specifics of its journey remain elusive. What forces guided it into its current orbit? Was it the gravitational influence of a larger planetary sibling, long since ejected or consumed? Did its migration destabilize other celestial bodies, scattering smaller planets or moons into interstellar space? Or was its inward slow spiral through the remnants of the disk? These questions a single shedding light on the forces that sculpt planets throughout the galaxy. Its atmosphere is not merely escaping, it is evolving. The hydrogen tail trailing behind is the most visible sign of a much larger phenomenon, that hills, including carbon and are also being lost, albeit at a This raises profound questions. Does this onus alter over time, be undergoing that will leave it unwrecked distant future? Do the processes at work in its atmosphere mirror potential atmospheric changes on other worlds, including Earth, under extreme conditions? The chemistry within this scorching environment is equally fascinating. Subjected to intense radiation, molecules are broken apart and recombined to challenge existing models. Temperatures and pressures, formation of exhaust, including metal-rich vapors and ionized. Could there be materials in its atmosphere that have no natural analogues on Earth, existing only under these extreme conditions? If so, studying them had insights not just into science but also into new free and materials research. The winds that sweep across this volatile world add another layer. Currents, driven contrast between the night and night side, chaotic and ever-changing. In recent models suggest that massive jet streams encircle the planet, transporting heat and chemicals in unpredictable patterns. These could give rise to anything seen in the solar system. Transient atmospheric reaction, are they simply another expression of the sheer chaos that defines this exoplanet? Beneath its roiling atmosphere lies a hidden core, a realm beyond direct observation yet central to understanding its history. What resides within? Is it a dense, rocky center like that of Jupiter, or does it harbor exotic materials forged under the immense pressures unique to hot Jupiters? Some researchers speculate that the core might contain superionic water, a phase of matter where oxygen atoms form a solid while hydrogen ions move freely, existing simultaneously as both liquid and solid. Such an exotic state would not only redefine our understanding of planetary and also behavior of matter conditions. The presence of a magnetosphere adds another dimension of intrigue. If a strong magnet exists, it actually shield the relentless winds, slowing the rate of mass loss. However, such come at a cost. Interactions between the charged particles and this could generate immense electrical currents, lighting up the planet with auroras far more powerful than anything seen in our solar system. These glowing arcs of energy, could be the most striking visual testament to the ongoing struggle between the planet and its battle playing out in colors and light across its turbulent skies. Beyond its current state, this planet may offer a glimpse into the future of planetary evolution. While its extreme conditions make it inhospitable, the processes shaping it are not unique. Many stars will eventually evolve into red giants, engulfing their inner planets in radiation and stellar winds. Could this world be a preview of what might happen to planets like Earth as their stars age and expand? Could the atmospheric escape obscure clues about how the atmosphere might change under billions of years, elevate its significance from a singular curiosity to a crucial piece of the puzzle in understanding planetary evolution on a cosmic scale? This world also continues to inspire the search for other exoplanets. Its discovery and the techniques developed to study it have paved the way for identifying thousands of new worlds, many of which now await detailed observation. With advanced instruments like the James Webb Telescope and upcoming missions, scientists to explore planets that are smaller, cooler, and potentially more Earth-like. Yet even as attention shifts to these more temperate candidates, the study of extreme worlds remains invaluable. The searing heat, chaotic winds, and evaporating atmosphere of HD 209458b are testaments to the sheer diversity of planetary systems and the unrelenting creativity of the cosmos. Story. With every new observation and every refined model, more of its secrets are unveiled. Yet new questions always arise. It is a world of extremes, a living experiment in planetary physics, chemistry, and evolution. As exploration continues, this exoplanet remains a symbol of our quest to understand the cosmos, a reminder that even the most hostile environments can hold beauty, mystery, and the promise of discovery. To think bigger, to push the boundaries of our knowledge, and to embrace the infinites that await us among the stars. H9458b, or Osiris, is a masterpiece of cosmic extremity, a world that dances precariously close to the boundaries of destruction, yet thrives in its own relentless way. Its ongoing transformation and enigmatic properties make it one of the most studied and theorized planets in the universe. Yet, as much as we've uncovered, it feels as though we are still gazing through a fog, catching glimpses of truths that seem just beyond our reach. Osiris is not merely, it is by the universe itself, a puzzle that demands the attention of humanity's brightest minds. HD 2094, known as Osiris, astonished scientists with its defining evaporating atmosphere that visibly trails behind it like a cosmic signature. The vast comet-like tail of hydrogen is undeniable proof of the relentless radiation from its host star stripping away its outer layers. But this is only the beginning of the story. The detection of heavier elements, oxygen, carbon, and even traces of metals, escaping the planet's gravitational grasp hints at an even more complex and long-standing transformation. How long has this process been reshaping the planet? Could it once have harbored a much denser atmosphere, or perhaps even moons, now lost to the slow yet unyielding forces of stellar radiation? The evolutionary trajectory of this gas giant questions. Current estimates suggest that while it will take billions of years to be stripped entirely, the cumulative effect will inevitably reshape it. Are we witnessing a brief moment in the lifespan of a will remain eroded rocky core of its past, or will it dissolve completely, leaving only the elements it contributed to interstellar space? The chemistry within its turbulent skies adds another layer of mystery. Water vapor, methane, carbon dioxide, and sodium have been detected, but these may only scratch the surface of a much more intricate and exotic composition. Under the planet's extreme conditions, radiation bombards molecules, breaking them apart and recombining their fragments into new chemical species that may be fleeting and temperate environments. Could these high-energy reactions serve as precursors to the complex chemistry seen in cooler, less hostile settings? Some researchers speculate that, despite its inhospitable nature, this world may provide insight into the very building blocks of chemistry itself. In Earth's early history, lightning and solar radiation played a role in synthesizing organic molecules, the precursors to life. Could Osiris's upper atmosphere, though vastly more extreme, offer a high-energy analog, allowing scientists to study how matter behaves under some of the most intense conditions in the universe? Even if no life could survive here, understanding how molecular structures form and evolve under such duress could reveal new pathways for chemistry across the cosmos. Beneath its volatile atmosphere, another puzzle emerges. Osiris's bloated size, 1.4 times the radius of Jupiter, defies expectations given its mass. Something gravity planet beyond models predict. Theories idle heating due to its ohmic dissipation, where it interacts with atmospheric currents, generating internal heat. But what if the explanation lies deeper? Some researchers propose that the intense pressures and temperatures within could give rise to exotic materials, such as metallic hydrogen or superionic water, substances that behave in ways never Earth. If present, these exotic states of matter could shape everything from the planet's heat retention to its magnetic field, influencing its long-term stability and evolution. Unlocking the secrets of its interior could transform our understanding of gas giants, including Jupiter and Saturn. If a magnetic field does exist, its effects would be profound. A sphere could be of shielding the charged particles from and slowing atmospheric escape. Such a force would also have unintended consequences. The interactions between the magnetic field, ionized gases, and stellar radiation could generate massive electrical potentially creating planet-wide auroras storms of unprecedented scale. If such auroras exist, they would be unlike anything seen on Earth. Rather than soft, flickering waves of green and blue, these would be violent energy, stretching across the entire night side, visible even from interstellar distances. The unique atmosphere could give rise to colorful reds, deep purples, or even metallic hues. If observed, would offer a dramatic visual representation of the constant between the planet and its star. Osiris's current proximity to its host star suggests a dramatic past. Theories of planetary formation indicate that gas giants like this one form much farther out, where cooler conditions allow volatile compounds to condense. For it to have reached its perilous orbit, it must have migrated inward, a journey that would have been anything but peaceful. Did it interact with other planets, ejecting them from the system or even consuming them? Could it have destabilized an entire planetary neighborhood in its relentless inward drift? Scars of this journey may still be imprinted in its composition and structure. Its core could hold remnants of the materials it encountered, while its atmosphere might carry traces of other celestial bodies it disturbed or absorbed. Could it have once been part of a grander planetary system, now left fragmented by its gravitational influence? If so, it stands as both a survivor and a catalyst of destruction, a world that has endured the chaos it may have helped unleash. Looking forward, the fate of this planet remains in question. Its atmosphere will code, and its interaction will intensify as the star itself evolves. Will it shrink into a dense, lifeless core, a shadow of its former self? Or could it be entirely consumed by its sun, its final act of fiery dissolution into the stellar inferno? This relentless transformation serves as a stark reminder of the impermanence of even the most massive celestial bodies. Beyond its own destiny, Osiris offers a glimpse into the potential future of planetary systems like our own. As it will expand into a red giant, likely engulfing Mercury, Venus, and perhaps even Earth. The process is unfolding on this distant exoplanet may foreshadow the fate of worlds much closer to home, giving us a rare opportunity to study, in real time, the mechanisms that shape planetary on a cosmic scale. More than just a curiosity, Osiris represents the power of human ingenuity. Its discovery helped pave the way for modern exoplanetary research, and its study continues to push the boundaries of what we understand about planetary atmospheres, chemistry, and migration. It serves as a reminder that the universe is far stranger than we can yet comprehend, its mysteries stretching beyond the limits of imagination. And in that strangeness lies the promise of discovery, the thrill of the unknown, and the relentless pursuit of understanding the worlds beyond our own. HD 209458b stands at the edge of what we know about planets, constantly inviting us to push further into the unknown. It is a world of contradictions, caught in a cycle of relentless destruction yet displaying extraordinary endurance, a chaotic battlefield of forces that somehow maintains an intricate cosmic balance. More than just a scientific curiosity, this distant exoplanet challenges not only our understanding of planetary science, but also our perception of what is the universe. Ongoing transformation is a testament to nature and the unprecedented shape of the galactic scale. As its atmospheres emerge, what happens to the lost material? While hydrogen disperses into interstellar space, heavier elements such as carbon may linger, forming transient clouds or interacting with stellar winds to create unexpected structures. Could this be an invisible trail, a legacy of its atmospheric unraveling etched across its system? By studying this, scientists uncover secrets about its chemical history. The ratio of hydrogen to heavier elements in the planetary tail may reflect conditions during its formation. Was this gas giant originally enveloped in a more complex atmosphere, or has it always been predominantly hydrogen and helium? Reconstructing its past through its evaporative footprint could provide key insights into how similar planets evolve. The extreme heat of its day side, soaring beyond 1,000 degrees Fahrenheit, a furnace-like reshaping atmosphere is yet to be full. Radiation not only ionizes the gases, creating an electrically charged environment. Weather patterns may unfold. Metallic clouds dissipate, winds sweep across the planet at unimaginable speeds. Some models suggest that this turbulent system functions like a planetary heat engine, redistributing energy unpredictably. Certain atmospheric layers may act as temporary barriers, forcing heat to escape in bursts and generating shockwaves. These violent disturbances could explain some of the spectral variations observed, hinting at a dynamic and volatile climate. Beneath the chaos of the upper atmosphere, even greater is hidden. The core is more than just a foundation. It is a time capsule preserving the conditions underformed billions of years ago. Could it be enriched with heavy elements, scarred by a violent migration? Or does its composition suggest a more gradual evolution? Some scientists speculate that tidal interactions with its star may have the core, contributing to its inflated size. If true, this would make its interior one of the most unusual in the known universe. Beyond its atmosphere and core, this world may produce breathtaking displays of light. Charged particles from escaping gases, interacting with stellar radiation, could generate auroras far beyond anything seen in our solar system. Outside, bathing perpetual glow visible for systems. Its evaporating atmosphere may also shimmer with ionized gases, forming a ghostly halo around the planet. Hence hydrogen glowing remnants could make this gas giant one of the most visually spectacular objects in its system. If only we could see it up close. Yet this is not just an object of study, it is a planet in the midst of profound change, and its impact may extend far beyond itself. As mass is lost, the escaping material could seed nearby space with elements that may one day contribute to the formation of new stars and planets. In this way, it is not merely but a participant in the cosmic cycle of creation and destruction. Its story also forces us to consider the planet's other hot Jupiter's ring but common phase evolution. How many similar worlds are under transformations, their atmospheres dissolving unnoticed in distant star systems? The study of this extreme compels us to look beyond a single planet and contemplate the unseen dramas playing out across the universe. The most profound lesson it offers is not about its atmosphere, core, or migration but about perspective. What does this distant world teach us about our place in the cosmos? It exists in conditions wholly alien, yet its study reveals principles, gravity, energy, motion, and chemistry that apply everywhere. In this way, it is both familiar and alien, a reminder that while planets may differ in their extremes, they are all fundamental forces. To define our methods of planetary observation, this world remains a beacon, a symbol of the challenges and rewards of venturing beyond our solar system. It shows us that even in the harsh, forgiving environment, complexity, beauty, and a story waiting to be told. It pushes on what might lie beyond distant worlds, and to embrace the boundless possibilities of the universe. Its story is far from complete. With each new observation model and through, we understand every answer we uncover, new mysteries arise, ensuring that generations to come. More than just an exoplanet, it reflects processes cosmos, destruction, trend renewal. It embodies a paradox, a planet losing itself to its star, yet persisting, a world operating at the extremes, yet governed by universal laws, a system that reveals enigmatic hot Jupiter is not merely an object of study but a teacher, guiding humanity toward deeper understanding, not just of distant worlds, but of our own place in the vast, unfolding cosmic narrative. The ongoing study of this planet serves as a powerful reminder that planets are not static entities. They evolve, interact themselves over time, influenced by govern their existence. Through its dramatic atmospheric loss, this gas giant illustrates the delicate planet and its star relationship that of many worlds, including our own. Its story also challenges us to consider the long-term destiny of planetary systems. The forces stripping its atmosphere today will one day affect, including those. The sun ages and expands into a red giant, it will engulf Mars, and could it, in some far-off system, one day witness undergoing a transformation? If so, gain now may help even prepare for the planetary descendants. But beyond science, this exoplanet represents something more, the relentless human drive to explore, to push beyond the boundaries of knowledge, and to understand the worlds beyond our own. Its discovery in 1999 marked a turning point in exoplanetary science, helping to establish the methods that have since revealed thousands of distant worlds. It showed us that planets could exist in extreme conditions, that atmospheres could be studied across vast distances, and that each new discovery would only expand our sense of what is possible. In many ways, this hot Jupiter is a symbol of human curiosity. Its study has led to technological advancements, inspired new research, and helped reshape our understanding of planetary diversity. It has set the stage for the next generation of explorations, Webb Space Telescope to future missions of habitability and even life beyond Earth. As we continue to study this distant giant, we are reminded of the beauty of exploration itself. A world with fiery winds and an evaporating atmosphere challenges us to think beyond our own, to confront the unknown, and to embrace the vastness of the cosmos. It forces us to ask deeper questions. How do planets like this evolve? What can they teach us about the origins of our own solar system? And what other marvels await discovery among the stars? Its story is not one with a final answer, it is an ongoing journey, one that will evolve as our tools improve, our knowledge deepens, and our imagination expands. It stands as proof that science is not about reaching conclusions but about embracing the process of discovery, one as infinite as the universe itself. As it develops more advanced telescopes and exploration missions, the secrets of this fascinating world will continue to unfold. Its atmosphere, core, and dynamic interactions with its star will reveal new mysteries, each more precise. And though we may never fully understand its intricacies, its study will continue to inspire future generations of scientists, dreamers, and explorers. This planet is not just a distant object in the cosmos. It is a bridge between the known, a testament to the power of curiosity and the thrill of exploration. It carries the story of a universe alive with possibilities, a universe that beckons us to explore and to dream. very close to their stars. Discovered in 1999, it was the first exoplanet confirmed through the transit method, where the planet passes in front of its star from our perspective, causing a temporary dip in brightness. This breakthrough not only secured its place in astronomical history, but also marked a turning point in the study of distant worlds. Also known as a transiting exoplanet, HD 209458b is about 220 times more massive than Earth, with a approximately 1.4 times that of Jupiter. Despite its size, it orbits its star at an extremely close distance of just 0.045 astronomical units, AU, which is 1/8 the distance between Mercury and the Sun. This proximity results in extreme atmospheric heating, with temperatures soaring to around 1,000 degrees Celsius, 1,800 degrees Fahrenheit, making it a classic hot Jupiter. One of the most remarkable aspects of this exoplanet is its atmosphere. It was the first where scientists Sodium was the first element identified, offering an initial glimpse into its composition. Later studies revealed the presence of water vapor, methane, and carbon dioxide, making it the first exoplanet with a multi-component atmospheric analysis. Another crucial discovery related to HD 209458b was its atmospheric escape. Observations from the Hubble Space Telescope revealed that the intense radiation from its star is stripping away the outer layers. This process, known as hydrodynamic escape, has created an enormous cloud of hydrogen trailing the planet, resembling a comet's tail. Due to this phenomenon, it was dubbed an evaporating planet. The estimated escape rate is about 10,000 tons of hydrogen per second, a significant loss, yet not enough to deplete its mass within billions of years. The planet has also played a major role in understanding cloud formation in extreme environments. High altitude hazes and potential cloud structures inferred from its spectrum suggest the presence of scattering particles in its upper atmosphere. These findings have provided valuable insights into the physics and chemistry of exoplanetary atmospheres, helping refine models for other distant worlds. Another fascinating is its orbit. With an incredibly short orbital period of just 3.5 days, its proximity to the star generates strong tidal forces, likely causing it to be tidally locked. This means one hemisphere is in perpetual daylight, while the other remains in eternal darkness. The extreme temperature gradient between the two sides results in violent atmospheric dynamics, including supersonic winds that redistribute heat. Beyond its scientific contributions, this exoplanet has played a key role in advancing observational techniques. Its discovery pushed the limits of spectroscopy, transit photometry, and atmospheric modeling. Initially confirmed via the radial velocity method, which detects a star's wobble due to an orbiting planet's gravity. It was later studied using both radial velocity and transit methods. This dual approach allowed for unprecedented precision in determining its mass, radius, and density, setting a new standard for exoplanet migration. Like this one did not form in their current orbit, but migrated inward after forming farther from their star. The exact mechanisms, whether interactions with the protoplanetary disk or gravitational influences from other planets remain an active area of research. Studying this planet and similar ones helps refine models of planetary evolution. Another intriguing challenge posed by this exoplanet is its unexpectedly large size. Its radius exceeds predictions based on standard planetary models, an issue known as the radius anomaly, which is common among hot Jupiters. Several explanations have been proposed, including additional heat sources such as tidal heating or ohmic dissipation, where magnetic interactions between the planet and its star generate extra energy. Continued research on HD 2091 9.458b provides valuable clues about these complex processes. Beyond its direct scientific impact, this planet has become a cultural and inspirational symbol in the search for extraterrestrial worlds. Its discovery and revelations about its atmosphere, orbit, and physical properties have captivated both scientists and the public. As a pioneering exoplanet, it represents how far humanity has come in exploring the universe beyond our solar system. In conclusion, HD2094588B remains a landmark discovery in modern astronomy. Its detection marked the beginning of a new era in exoplanetary science, and its detailed study has provided essential knowledge about planetary atmospheres, migration, and evolution. As a hot Jupiter gradually losing its atmosphere to its star, it serves as a natural laboratory for studying extreme planetary environments. The legacy of this exoplanet lies not just in what it has taught us about a single world, but in how it has paved the way for the exploration of countless others documented and fascinating exoplanets ever discovered. Orbiting the star in the constellation Pegasus, this gas giant is located approximately 150 light years from Earth. Its discovery in 1999 was groundbreaking, as it became the first exoplanet observed transiting its host star. This key observation allowed scientists to study not only its orbit, but also its physical and atmospheric characteristics in unprecedented detail, making it a cornerstone in the history of exoplanetary science. Often referred to as the pioneering hot Jupiter, HD20945B has a mass roughly 220 times that of Earth, or about 0.7 times that of Jupiter. However, its radius is significantly larger, approximately 1.4 times that of Jupiter, classifying it as an inflated planet. This unexpectedly large size and low proximity may contribute to this inflation, a trait observed in many hot Jupiters. The exoplanet follows an extremely tight orbit, circling its star at just 0.045 units and completing a full revolution in only 3.5 Earth days. This close range exposes it to immense stellar radiation, heating its atmosphere to over 1,000 degrees Celsius, 1,800 degrees Fahrenheit. The extreme heat causes the atmosphere to expand and escape into space, burning at the classification of an evaporating planet. Observations from the Hubble Space Telescope have revealed a vast cloud of hydrogen, along with traces of oxygen and carbon, trailing behind the planet like a comet's tail. This large-scale atmospheric provides valuable insights into the evolution of planetary atmospheres. The atmospheric composition of this exoplanet has been a major focus of scientific research. It was the first where atmospheric components were directly detected, setting a precedent for the study of exoplanetary atmospheres. Early observations identified sodium, but later studies revealed the more complex mix. vapor, methane, and carbon dioxide. The detection of water vapor was particularly significant, as it marked the first confirmed presence of water on a planet outside the solar system. This finding demonstrated the potential for detailed atmospheric analysis of exoplanets, even those located light years away. Beyond its chemical composition, the planet's atmosphere exhibits extreme physical dynamics. It is believed to be tidally locked, with one hemisphere in constant daylight, while the other remains in perpetual darkness. This sharp contrast creates a dramatic temperature gradient, generating supersonic winds that may reach speeds of up to 7,000 kilometers per hour, 4,350 miles per hour. These winds redistribute heat across the planet, leading to turbulent and complex weather patterns. Observations have also suggested the presence of high-altitude clouds and hazes, further complicating its atmospheric behavior. The study of HD 20945b has provided crucial insights into planetary migration. Current models suggest that hot Jupiters like this one did not form farther from their stars. The mechanisms responsible for this migration, whether interactions with the protoplanetary disk or gravitational influences from other celestial bodies, remain an active area of research. The extreme proximity of this exoplanet to its star challenges existing theories and continues to prompt new investigations into the forces shaping planetary systems. Another enigmatic aspect of this world is its unexpectedly large radius. Standard planetary models struggle to explain this inflation, as its size exceeds expectations based on its mass and temperature. Possible explanations include tidal heating, where gravitational interactions with the host star generate internal heat, or ohmic dissipation, a process in which the planet's magnetic field interacts with ionized gases in its atmosphere, converting kinetic energy into thermal energy. The precise mechanisms behind this inflation remain a subject of ongoing research. This exoplanet has also played a key role in advancing observational techniques. Its discovery and subsequent characterization relied on a combination of the radial velocity method and transit photometry. radial velocity method detects the gravitational wobble of a star caused by an orbiting planet, while the transit method measures the dip in a star's brightness as the planet passes in front of it. Together, these techniques provide extensive details about the planet's mass, radius, orbital period, and atmospheric properties. This dual method approach has since become a standard in exoplanetary research, facilitating the discovery and analysis of thousands of distant worlds. The significance of HD 209458b extends beyond its own unique characteristics. Its discovery and extensive study have paved the way for further exploration of exoplanets, inspiring the development of new observational tools. For example, the James Webb Space Telescope (JWST) is expected to build upon its legacy by offering even more detailed observations of exoplanetary atmospheres. The techniques used to analyze this gas giant influenced the design of upcoming projects, such as the European Space Agency's aerial mission, which aims to examine the atmospheres of hundreds of exoplanets. In conclusion, HD 58b, often referred to as the evaporating planet. The roaster world, or the inflated gas sphere, remains a landmark in the study of exoplanets. Its discovery marked the beginning of a new era in astronomy, while its detailed characterization has provided unparalleled insight into planetary atmospheres, migration, and evolution. As one of the most thoroughly studied exoplanets, it continues to serve as a natural laboratory for exploring the physics and chemistry of extreme planetary environments.